The first example that we looked at was really challenging and actually pretty complex. So there was a lot going on here. In this example, we're going to look at a much simpler example, something that we can work through a little bit quicker. So let's suppose that we have a point that is moving along the graph of y cubed equals x squared. When the point is at -8, 4, its y value is changing by 2 units per second. I want to know how fast is the x coordinate changing. So my first step here would be to draw a picture. Now, if you wanted to, you could actually go and look at the graph of y cubed equals x squared. Although, to be honest, for this problem, I don't think it's actually going to be particularly helpful. So I'm actually going to skip that step here. I'm not going to draw myself a picture, but I am going to, in my second step, identify all of my variables and label them out. I'm going to lay out all of the information that I can get from this problem. And in this case, we're actually given the equation that relates our two variables. We've got y and x. Those are what we have. So we've got x and y. And as far as the values that those take on, well, I can just look at the ordered pair that was given to me. We're working with the point -8, 4. So that means x must be -8, y must be +4. In this case, I've only got the two variables. I know exactly what values they're taking on at this particular moment in time. So that's all I really need to do for this second step. My third step, we wanted to talk about the derivatives of each of these variables and express any rates that were given to us as derivatives. So I'm going to want to know what is dx over dt, or x prime, and what is dy over dt. What values are those? So I'm going to look for any rates of change that were given to me in this problem. Well, this says its y coordinate is changing by 2 units per second. So it tells me that the y coordinate is changing by that, so that's going to be the derivative of y. And it says by 2 units per second. I'm going to assume it's a +2, so that means that dy over dt is equal to 2. We want to know how fast is the x coordinate changing, which means that dx over dt, that's going to be what we solve for here in this problem. So this is, even though we don't have a picture, I still think this is a really important step, and a really helpful step is to just write out everything that the problem gave to you in an easy to read format and an easy to find format, so that we can find all of this information without having to go back and reread the problem. So that was steps 2 and 3. Step 4, we want to come up with an equation that relates our variables. And in this case, well, we don't have to come up with one because it was just given to us. We're working with the graph of y cubed equals x squared. So I know that my equation is going to be y cubed is equal to x squared. There is my equation. Once I have that equation, step 4 says take the derivative with respect to time. So I want to take the derivative of both sides of my equation now with respect to time t. Now, neither one of these is written with respect to time t, so I am going to have to use implicit differentiation. I am going to have to use the chain rule here. So the derivative of y cubed using my power rule, well, that's going to be 3y squared, times the derivative of y with respect to t, that would just be dy over dt, is equal to, now I want the derivative of x squared, which would be 2x using my power rule. But again, x is a function of time, so that means I need to multiply by the derivative of x with respect to time, or dx over dt. So here I have my derivative. I've got 3y squared times dy over dt is equal to 2x times dx over dt. And now I can take all that information that I laid out so nicely before and just plug that into the derivative that I found. So let's do that. 3y squared, we said y was 4, times dy over dt, we said that was 2, is equal to 2 times x. Here in this problem, x is negative 8, times dx over dt. We didn't know what that was, so we'll just leave that as dx over dt. So now we've just got some multiplication to do. 3 times 4 times 2 here, I should have 24 is equal to 2 times 8, negative 16 times dx over dt. And then I'll just divide both sides by negative 16. So that means that dx over dt is 24 divided by negative 16. If we want to give it decimal, that's okay too. Here we have negative 1.5. So here is our dx over dt. I would like to give a unit on this. So in this case, I want to think about what are the units of x. And in this case, I can kind of look at the rate that was given for y. And here we said we were working with a rate of change of 2 units per second. So I know x is going to be measured the same way. So negative 1.5 units per, and my unit of time in this case would be seconds. So negative 1.5 units per second. If I wanted to go one step further, I could actually interpret this, and I can look at that and say, well, because it's negative, that means the x value is decreasing by 1.5 units per second at the point we said negative 8, 4. So that's actually what's happening, is the x value is decreasing by 1.5 units per second. Most of the problems that you'll be doing in my math lab, you'll probably just need to give a rate in this case, so units per second. That would be enough. But if I want to think about what that means and just take it one step further, I do think that's a really helpful approach and a really practical approach when we look back and think about our answer, what it is that we've actually solved for.